Hi there, in this video I will teach you how to solve linear recurrence relations with constant coefficients. And we will see that solving a recurrence relation is a lot like solving a differential equation. So this is almost same as solving a differential equation of the same type. y2 prime minus 3y prime plus 2y is equal to 0. So when we have a differential equation like this, we would say let the solution be in the form of y is equal to e to the rx, and then we would just differentiate it and put it in the equation, and we would get r squared minus 3r plus 2 is equal to 0. And then we would just, according to the values of r, we would separate it into 3 cases and we would solve it. And here we are going to do exactly the same thing, and we will guess the solution being in the form of r to the n. Where does this r to the n come from is actually easy. Imagine we have a sequence like an plus 1 is equal to 2 times a to the n. So we are just multiplying each term by 2. Okay, so it will be just exponential of 2 to the n, and we may begin with any constant of a. Imagine the first one, if a0 is just 5, it will be 5 times 2, 5 times 2 to the 2, and it will be 8 times 2 to the n in general. And so this is where it comes from. If we have this factor being 2, here all of them are 1, but if I have multiple terms like this, I don't know if it's going to be 2 to the n. So in general, we just guess it's like in the form of r to the n. And then if we substitute it in here, we will again get the same thing. R squared minus 3r plus 2 is equal to 0. This is our characteristic polynomial. And then we just solve it. So it's just r minus 2 times r plus r minus 1. So r is equal to 1, r is equal to 2. Let's call these r1 and r2. And then we say our general solution is just an, a constant times r1 to the n, let's say a times 1 to the n, and plus b times r2 to the n, b times 2 to the n. And this is going to be the same case even though, like, no matter which degree does this polynomial have, it will always be at the same logic. And then we can solve this equation with this initial values. So if I put n is equal to 0, I will get a plus b, and a0 is equal to 1. And if I put n is equal to 1, I will get 3. So if I put n is equal to 1, a plus 2b, this is equal to 3. So I have a difference of b and 2. So I can say this b is equal to 2 and a is equal to minus 1. So that's it. I found that an is just, so I have 2 times 2 to the n. It will be 2 to the n plus 1 minus 1. And this is my answer. And so this was the case when we have different roots. And if we have same roots, it will be again similar logic with differential equations. So if I say, if I consider the characteristic polynomial of r squared minus 4r plus 4, this is r minus 2 squared. And so I can say that r is equal to 2, but this is double root. So I will have an is equal to a constant times 2 to the n, again just r to the n, and here instead of having b times 2 to the n, we will get another constant of b, another factor of n. And why is it the case? Because if we had a differential equation like this, we would say it will be just a, let's say it's e to the 2x, it was gonna be c1 plus c2, but it's not gonna be c1 plus c2, c1 plus c2x. So here it's same analogy, n is treated like this x. And so this was the case when we have two same roots, or it can be any number of same roots. But if we have complex roots, it's not that easy to solve it like differential equations, and we get periodic solutions, and I'm not going to consider them in this video. And let's consider an easy example and finish this video. So let's consider this really easy Fibonacci sequence. Imagine we have 1, 1, 2, 3, 5, 8, and it's going on like this. This is the Fibonacci sequence, and it's defined as, let's say, an plus 1, an plus 2 is equal to an plus 1 plus an. So I'm just adding two previous terms to get the next term. And I can say, let's say a0 is equal to 0. Let's start it with 0. It doesn't matter. And a1 is equal to 1. So, and to make it work, I need to send everything on the left side. So I will have r squared minus r minus 1 is equal to 0. And if we solve it, so this is just going to be 1 over 2, 1 over 2, and this will be just 1 over 4 minus 1, so it will be just 5 over 4. So it will be 1 plus minus square root of 5. And so I have this. This is actually similar to golden ratio. This is the positive root is golden ratio. And so I can say my general solution of an, it's going to be a times a constant, the first root, 1 plus square root of 5 over 2 to the power of n, and plus b times my second root, 1 minus square root of 5 over 2 to the n. And I also have these initial values, so I can solve it for a and b. So if I put n is equal to 0, I will get, so these things are just going to make 1. So a plus b is equal to 0. So I know that a is equal to minus b. And if I put n is equal to 1, this is just going to give me this thing plus this thing. Let's write it. So I have a times this thing, square root of 5 plus 1 over 2, and plus b, 1 minus square root of 5 over 2. So here, if I just substitute a is equal to minus b, let's put it here, a is equal to minus b. So I will get in b parentheses, I will get this thing, 1 minus square root of 5 over 2. And so this will be just multiplied by minus. So this will be plus minus 1 minus square root of 5 over 2. And this is going to be equal to 1 because a1 is 1. So this is 1. And if I do it, so this and this will cancel out. So this will be minus 2 square root of 5. And I will also divide it by this. So it will be b times square root of 5 is 1. So b is minus 1 over square root of 5. And b was minus a. So I can say a is 1 over square root of 5. And this is my answer. So if I just write the solution, this is going to be, so a is, if I have 1 over square root of 5 parentheses, and I also have 2 to the n, let's also take it here, 2 to the n, and I will have, let's delete this thing, so I have 1 plus square root of 5 to the n, and so I have, this is going to be minus 1 minus square root of 5 to the n. And this is general formula for the nth Fibonacci number, and that's the answer.